what we're going to do in the next section is to use these models, both the well mixed room model and the near field, far field room model in real life scenarios. In the first scenario, scenario one, what's happening is there is 100 centimeter squared piece of some super reflective tape that is made by a company. And one of the employees, John, uses an FTIR instrument to derive an off-gassing rate for toluene from this tape. However, he's not super confident about this off-gassing rate, so there is some uncertainty there. And we'll talk about this in a second. You are selling small rolls of this tape that are 12 inches wide and 16 inches diameter to a customer who stores them as inventory in a workroom. And the dimensions of the workroom are 30 feet by 30 feet by 20 feet. And the ventilation rate through this storage area is very low. It's 0.1 air changes per hour. If the customer receives a full shipment of 30 rolls on a Friday, and they are put in the storage room and the doors are all locked on a Friday, and the concentration we can imagine would build up over the weekend. And so what would be the maximum concentration that occurs over the weekend? And how do we go about modeling such a scenario? So we can look at this scenario as, since there is off-gassing from the tape, we can use the well-mixed room with exponential decay as our starting point. So the volume of the room is given by 30 feet by 30 feet by 20 feet. And there is about 0.3 meters per foot. So we can convert the cubic feet to cubic meters for the volume of the room. So we get 509 cubic meters as the volume of the room. So how do we model the mass of contaminant, in this case toluene, on the rolls of this tape? So let's assume that there is 1 milligram of toluene per 100 centimeters squared of the tape. That's what the FTIR experiment that was mentioned in the previous slide determined. There are 30 rolls, and so now we need to come up with the surface area of one roll of this tape. And so one simple way to do it is to say, okay, it's a cylinder, and so the surface area of one roll is modeled as 2 pi times the radius of the cylinder, which is 8 inches, and then the length of this is given by 12 inches. So 12 plus 8 times, convert the inches into centimeters, so that's the 2.54. And so you get 1,945 milligrams of toluene on 30 rolls of this tape. We don't know the evaporation rate exactly, but John's experiment using the FTIR gave an estimate of 0.2 per minute, meaning that 20% of whatever is on the tape evaporates per minute. And we will also assume that the ventilation rate is 0.1 cubic meters per minute. So we can put in these values of the parameters into the well-mixed room model with exponentially decaying generation source model and plot this equation. As we can see here, on the x-axis we have time in minutes for the entire weekend, and the y-axis we have the concentration in milligrams per cubic meter. And we can see that the concentration spikes very rapidly. So it goes up to 3.8 milligrams per cubic meter only after 60 minutes after you place the rolls into the storage room. And thereafter, it slowly decays over the entire weekend. And at the end of the weekend, it has reduced somewhat, but it is still around 2 milligrams per cubic meter. So this is what the well-mixed room model predicts for the concentration of toluene in the room throughout the weekend. There is another way in which we can think about the mass of toluene in the tape rolls. And so this is more to look at the rate at which contaminant is off-gassing from the source, in this case the tape. So now let's assume that each layer of this tape has a thickness of 1 millimeter. And it can be thought of as a cylinder of length 12 inches. And now the radius is varying from 1 millimeter for the first roll all the way up to 8 inches or 8 times 2.54 centimeters. So that is the outermost layer of the tape. And so now the total area of one roll is the area of all of these layers. And so that comes out to be 396,543 centimeters squared. And so now the initial mass of the toluene in these 30 rolls is 30 times 396,543 times 1 milligram per 100 square centimeters as before. So now we get a vastly greater amount of toluene as the initial mass. So now we are at 118,963 milligrams, whereas in the previous set of assumptions, we were at around 1900 milligrams. So we have almost an order of magnitude difference, almost 2 orders of magnitude difference between these two assumptions. But we need to now modify the evaporation rate because most of the layers of the tape are not open to the environment. We can imagine that the toluene in the inner layers are slowly migrating to the surface of the tape roll and then evaporating. And so the effective evaporation rate is much smaller than what we had assumed previously. So let's just assume that now it's 0.0002 per minute. And so now we get a completely different type of profile. Since our evaporation rate is very slow, the concentration, even though we are using the same model, the well-mixed room model with exponential decay, the concentration in the room is increasing throughout the weekend because of the slow rate of emission from the tapes. End of 4,000 minutes, the concentration in the room has reached around 80 milligrams per cubic meter. So now the person opening the workroom on Monday morning will get a significant whiff of toluene. So in the previous two slides, we had assumed that the evaporation rate in the first case was 0.2 per minute, and then we assumed that maybe it was as low as 0.0002 per minute. And obviously, that single measurement that John had made was not very precise. There's a lot of uncertainty in our knowledge of this parameter alpha. So we can use modeling to decide whether this uncertainty in our knowledge of this parameter alpha makes a significant impact on our modeling results. So when alpha is 0.2 per minute, we have the profile that is shown by the dotted line at the very top. So we have a sharp spike right away, and then there's a slow decay over the rest of the weekend. And at the end of the weekend, our concentration in the room is about 108 or 109 milligrams per cubic meter. Likewise, when we have an alpha of 0.0002 per minute, the concentration is now increasing, and it hasn't even reached its maximum as predicted by the well-mixed room model when the weekend is over and the employee opens the door. And so now the concentration has just reached about 84 milligrams per cubic meter. And we can also look at the effect of two intermediate values, alpha equal to 0.02 and alpha equal to 0.002 per minute. And we can see that they reach their peaks at different times over the weekend. But at the end of the weekend, on Monday morning, they have not very different concentrations. So if the question we are trying to answer is what is the exposure of the employee on Monday morning, then the effect of our knowledge of alpha doesn't play that big of a role because the concentrations on Monday morning are not that different from each other. They vary from 120 to maybe 108 or 109. Although if alpha is 0.0002, then we go down quite a bit to 84. But at least for the first three values, 0.2 to 0.002, the effect is not that significant. So we might say that we don't really care that much if we are wrong about our value of alpha. But if our question for our modeling is, when does the room reach its peak concentration over the weekend, then we see that the value of alpha plays a significant role. If alpha is 0.2, then the maximum is reached within the first hour. If alpha is 0.002, then the peak is reached at around 1200 minutes. And if the alpha is 0.0002, the peak is not even reached. In fact, the highest concentration is on Monday morning. So depending on the question we are trying to answer, the value of alpha is either very important or not important at all. And that is something we need to keep in mind when we are trying to do uncertainty analysis, which is a topic we'll start discussing in one of the later lectures. Namely, what is the effect of uncertainty on our model output, and what is the effect of uncertainty on the question we are trying to answer?